Surface area. Is two-dimensional. We calculate it by finding the sum of all the areas on the outside of the figure. And in general, it's a description of kind of like the what do I say here? Like the I don't want to say this. That's any value. Description of the. How about space? And kind of conceptually, it's a description of the space that's in contact with the outside. So when you think of surface area of figures, this kind of mostly comes into play. Like if you're thinking scientifically, we want to kind of know like a lot of like heat transfer and kind of weird things have a description or have a relationship between how much stuff is exposed to the outside world, and that's an idea. That's a surface area claim. Volume, on the other hand, is actually three-dimensional. Unlike surface area that can be kind of unraveled and described on a flat plane, what we saw with nets and our easy example of a pizza box, a volume doesn't have that property. A volume is very well, it only lives in three-dimensional world. There's not really a good two-dimensional description of it. Fundamentally, volume is simply just how much space a figure occupies. And common units. Cubic inches, cubic feet, cubic centimeters. In terms of liquid volume, does anyone know what a cubic centimeter is the same as? A milliliter. Now here's the real question. Now here's to go off of that. If the liquid volume is a liter, what would be our cubic analog here? Cubic meter? Cubic meter is like 80 million. Yes. In fact, it's 1,000 times bigger than a liter. Yes. Deciliter. Or decimeter, excuse me. A cubic decimeter is 1 liter. Notice how how this relationship arises. Notice how when the length unit goes up by a factor of 10, the the liquid volume unit goes up by a factor of 1,000, which is 10 to the third. It goes from a milliliter all the way to a liter. Kind of a nice, curious little scientific fact that maybe you could use in one of your projects or something. But. We're going to base, just like we based our study of lengths, just like we based our study of areas, we're going to base our study of volumes off of these three postulates. They are the three-dimensional analogs of all the two-dimensional and one-dimensional stuff. So we're going to, instead of, we base our areas off of area of a square, we're going to base volumes off of volume of a cube. In fact, a unit cube would be the best thing there, which is simply just length times width times height, or side cubed, or volume of a cube. Volume congruence postulate. If two polyhedra are congruent, then they have the same volume. We saw that idea in terms of area, and in terms of length. But probably the most powerful one, the one that we're going to use, that's going to be most handy for us, that we're going to invoke without really talking about it directly, is the volume addition postulate, which claims to us that if we want to find volumes of more complex figures, then all we really need to do is find a bunch of volumes, of simpler figures, and then be able to add them together so they don't overlap. Which is how we're going to attack most problems without really claiming the volume addition postulate. In its essence, volume is actually, I think, easier to calculate than surface area. The formulas tend to be a lot more compact. In terms of conceptually what we're doing, to calculate the volumes of prisms and cylinders, you can think of it as, if you thought of like one of the faces as like a sheet of paper, to calculate its volume, we're going to end up stacking a bunch of sheets of paper up, and then calculating and summing up all of the little areas, or little volumes, I guess would be more accurate, all the minuscule volumes that you'll talk about finding these volumes a lot more rigorously when you, in what's called analytically, with kind of more where these formulas come from. When you take a calculus course, maybe here at the high school, maybe when you leave and go off to wherever your future holds you. But for now, the formula is basically we're going to find the area of one of the faces, and then we're going to multiply it by the height. We're going to think of like stacking that many sheets of paper up or whatever. Again, this is a generalized formula for all prisms and cylinders. If you have a rectangular prism, this breaks down to your relatively familiar formula: length times width times height. But it doesn't have to be a rectangular prism. It very, very much could be a triangular prism, or a trapezoidal prism, or whatever. It's to calculate the area of the base, multiply by 10. And example A here on the backside.
Good morning, students.
Because the area of the trapezoid is 1/2 its sum of its bases times its height.
Okay,
and since
area of just one of the bases?
Yes.
Okay.
One base, and then we'll multiply it by, I don't know how many we have to stack. I guess you can think of it as how many you have to stack up. Not exactly that, but we're going to go out by 4. 9 plus 6. If this trapezoid, its bases are 9. So we add them together, multiply by 2, and then multiply by 15. In B, the cylinder. Cylinder is just a prism with a base as its circle. With a base as a circle. In this case, area of the base is pi r squared, which in this case is 9, times 6, which is, I believe, 81 times 6 is 486 times pi. Which is about in the neighborhood of 15 or so, 1.5.
6, 2, 6.
6.
I mean, 2, 6. 0.8.
Is approximately 1526 cubic feet. It's exactly 486 pi cubic feet. Again, it's helpful to be able to talk about both. The exact measurement is more helpful for calculations, but if we want to have an actual concept of how big, how much space is taking up, it can be much more useful than that. Either case will be fine. If I have some composite figures, it's again we're going to try to find areas or volumes, excuse me, of figures we know. I see two main candidates to try to find the volume here. You could say lob off this top rectangular prism and find volume up here and then volume below. I think another way that we'll try here is to cut off the side piece and then try to find this volume. By doing so, we need to divide this side length into two parts. This piece being 5. Therefore, this piece, the whole thing's 9. This is 5. This piece better be 4. So my strategy here will be to compute the two volumes and add together. The first volume being 4 times 4 times 5. The second volume being 5 times 4 times 2. And I believe we end up with, what, 20, 80, and 40 summed together to give us a grand total of 120 cubic units. In figure B, we have actually a large cylinder with a smaller cylinder that's been cut out of it. So we've really got like a pipe or like a tube of some sort. We're trying to find the volume of the tube where this pipe has been left over. So our strategy here, how about we find the volume of this large cylinder, and then let's take out the volume of this small cylinder that's on the interior. And what's left over should be the volume of this ring that's on the outside. Which ends up being, let's see, the volume of the large cylinder is pi times the radius squared times the height, which is 5. The radius of the large cylinder should be 7 plus 2 is 9. The volume of the small cylinder is pi times its radius, which is 7, times its height, which is still 5. To solve this exactly, I'd factor out the pi and the 5 from each of these. And you're left with this, which is 5 pi times 32. 5 times 32 is 160. The exact answer should be 160 pi cubic feet, I believe. Cubic inches. More useful in the real world sense here might be to find the approximate value and 160 pi. Can someone calculate that for me? It should be in the neighborhood of about 480 or so. 502. There's an approximate answer that's maybe a little more useful to us. 502.66 or so, depending on how you round cubic inches.